Okay, now let's consider which chelating agents are used for the analytical purpose. The deoxyperidoxime, yeah, that is very useful, but that's too expensive. So practically speaking, one must synthesize other chelating agents for metal ion determination. Okay, there are many types. Okay, so it depends. The you can synthesize any chelating agent. Okay, so there are numerous number of chelating agents, but practically, we can name these molecules. Okay, for example, NTA, nitrilotriacetic acid. Okay, it is tetradentate. Okay, tetradentate chelating agent because there are one, two, three, four arms. Okay, and this is also widely used. Okay, for specific purpose. I think this is a good for nickel ion complexation, and here EDTA. The full name is ethylene diamine tetraacetic acid. Okay, this is ethylene diamine structure, and there are one, two, three, four, four, yeah, tetraacetic acid. Okay, so this is hexa dentate. Okay, hexa dentate chelating agent. Okay, and this chapter especially concentrates on the EDTA, yeah, and its application, and the titration principle with EDTA. Another one is TCTA, trans 1,2 diaminocyclohexane tetraacetic acid. Okay, here this is also hexadentate chelating agent, but not not often used. Okay, and TTPA. Okay, this is what 1, 2, 3, 4, 5, 6, 7, 8 octa dentate chelating agent. I don't know who can use who used this chelating agent. And EGTA, let me see, let's count 1, 2, 3, 4, 5, 6, 7, 8. This is also octadentate chelating agent. Okay? Well, I'm not sure. you know I never heard that you know this chelating agent are used, but yeah, there must be. Okay? And for example, this NTA, it binds strongly the ion. Okay, this one, and three-dimensional structure is like that. And this one, TTPA, this one, when it binds the metal ion, yeah, it has this three-dimensional structure. Okay, but now let's concentrate on the EDTA. Yeah? This EDTA, this compound is cheap. Actually, is not very expensive. Actually, it's very cheap. So it's readily available. Okay. Okay. From now on, yeah, we'll consider EDTA only. EDTA is the most widely used complexing agent in analytical chemistry. Okay, you look at this structure closely. Okay, so EDTA is represented by the alphabet letter Y. Okay, Y is EDTA. Okay, Y, and strongly acidic solution. So all this molecule is fully protonated. Okay, for example, uh, this is a neutral EDTA. Okay, neutral state. Yeah? Although it has two negative charges on this carboxyl group, but there are also two positive charges on this amine group. Yeah, but if the solution pH is quite low in a strongly acidic solution, this one here, this oxygen, two oxygen atoms are protonated. Okay, so total charge is plus 2. Okay, 2 plus. Okay, and then the protonatable no, protons are 6. 1, 2, 3, 4, 5, 6. So we represent this form as H6Y2 plus. Okay, this one. This is fully protonated form of EDTA. So EDTA acts both as a complexing agent and as what? Acid. Yeah. This is what uh, hexaprotic acid. Okay. The maximum 6 protons are deprotonated from this structure. Okay. So EDTA now represented, fully protonate form H6Y2 plus. Yeah? And then look at this equation. And you have to know that once this EDTA binds the metal ion, the final form of a metal ion is this one, okay? Fully deprotonated form. Okay, here M, Y, N minus 4. The metal ion, the oxidation state is N plus, okay? Here, this one. You understand? And this is the actual form when coordinated with metal ions, okay? And especially for this one, this reaction, we write the formation constant Kf. Yeah? The equilibrium constant in this case is called formation constant, 형성상수. Okay, by definition we can write it this way, right? Okay, so the properties of EDTA, it is hexaprotic acid. Okay, so we can write step wisely from K1 to K6. Okay, it forms amazing thing of EDTA is that it forms a one-to-one complex with most metal ions. You see, that is very amazing thing. Only one-to-one complex is formed. Okay. Oh, by the way, here this one is there are 6 equilibrium constant. Okay, pK1 is 0. So this form is a very strong acid, and pK2 is 1.5, pK3 is 2.0, and pK4 is 2.66. Okay, and the protons are from this one. Okay, carboxyl proton are deprotonated, and pK5 is 6.16 and pK6 is 10.24. Okay, these two protons are from this amine proton. Okay, so formation constant Kf is usually very large. This one is very large. Okay, much larger than you expected. Okay, and it has 7 different forms depending on the solution pH from this hexaprotic form, this fully protonated to fully deprotonated. Okay, so forms are 7. Okay, so metal complex form is this one, M, Y, N minus 4. Okay, this one. Okay, so for since this one, this portion of fully deprotonated form is important, so we can write this alpha for y4 minus. Okay, by definition it can be write this way. This denominator is the what total concentration of EDTA. It takes 6 different forms, so the sum of all these forms is the formal concentration of EDTA. Okay, and this one, the numerator is only y4 minus concentration. Okay, and so instead of writing these 6 different forms like this, we simply write this way, bracket EDTA bracket. Okay, this is the total concentration of all free EDTA species in solution. Okay, this is important is that this is free. This free EDTA. Free means not complex to metal ion. Okay, here there's no metal ions here. Okay, this is a free EDTA form. Okay, and since this EDTA is an acid from acid-base chemistry, we can write this one alpha y4 minus equals the K1 times K2 times down to K6 divided by this one. Although the this equation looks quite complicated, you know the principle how to write this alpha, this what fraction, yeah? Fraction depending on the pH. Okay, it is given by this one. So look at this figure. This is a fractional composition of each species. Yeah, there are 1, 2, 3, 4, 5, 6, 7 species. Okay, depending on pH. Okay, at a very strongly acidic condition, this one, this species is here. H6Y2 plus, yeah, its portion is like that, and as pH increases, and then this one H5Y plus species increase and then decreases rapidly, and then H4Y, and then H3Y minus, and like that. Okay, and especially we are interested in the fractional composition of Y4 minus here. Okay, this one as high pH, mostly the EDTA exists as this form, but pH decreases. Okay, this one decreases rapidly. Okay, but that doesn't matter actually. Okay, uh, and the table 12 dash 1 uh, this table shows the alpha 4 minus values depending on pH. Okay, at high pH like pH 14 or 13, the this alpha fraction is 1. Okay, and as pH decreases, alpha value decreases rapidly. Okay, and at the pH 5, for example, it is only 2.9 times 10 to minus 7, very small. Yeah, and extremely at extremely acidic condition, alpha value is very small, become very small. Okay, and here I have to say something very important. Okay, in this case, although you can write the formation constant as this, but um, when you see this equation, you may say that only y4 minus form reacts complex with metal ions, not other forms. Like you may think that this one, other these forms except y4 minus don't have complex with metal ions. You may think that way. That's what I thought when I was college student. That made me a lot of very confused. But that is not true at all. Okay, you see, for example, this form y2 minus, this one also can have a complex with metal ions. Okay, but what's the difference in this case? You know the metal, when this one complex with metal ions, the two protons are removed. Okay, and then final form of complex is this form. Okay, yeah, you know you have clear, let me see, but it's not here, let me see. Okay, yeah, so you have you must not be confused of that. Okay, any form in principle, any form can have complex with metal ions, but final form, after complexing with the metal ions, is this one, this form. Okay. Okay, here's an example. What is the meaning of alpha 4 minus? Okay, at pH 6, at the formal concentration of 0.1 molar, the composition of EDTA solution, yeah, at pH 6.0, we can calculate in each fraction uh, for each species using you see, for alpha 4 minus you can use this equation, and for this one, alpha h6 y2 plus, the denominator is the same but the numerator is different. Okay, for this species numerator is this one. Okay, for this one and numerator this one. Okay, like that. And then at pH 6, this form exists. This concentration is what, 8.9 times 10 to minus 20 molar. Okay, very small. Okay, and uh, you can calculate all these species at pH 6. Let me see, 6 here. Which one is the most abundant? Maybe H2Y2 minus and the HY3 minus. Yeah, these forms are available. Yeah, yeah, most abundant species. Okay, here. So let me see this one. Okay, mm, Y2 H2Y2 minus is 0.057 molar. Okay, very large. And also this one takes 0.043 molar. Okay, so it is about 57%, because the total concentration, formal concentration, is 0.1 molar. Okay, this one takes us 47 3%. Okay, and Y4 minus, it takes this much. All right, this concentration, quite a low concentration. So alpha 4 minus is uh, this denominator is 0.1 molar. Okay, you add all this up, or since already the formal concentration was given, okay, 0.1 molar. The denominator is 0.1, and numerator is, you put this one. Okay, and then you'll find at pH 6, alpha 4 minus, the fraction is 1.8 times 10 to minus 5. Here pH 6, you see, you got this number, right? Yeah, like that. Okay? And then if you want, you can using this equation, you can calculate all the alpha 4 minus the fraction at these pH values. Okay.